So, same reminders as before. Final project team names due this weekend. I'm going to do on Saturday. I've started to create those groups. So if you've submitted your team names, I've created the little individual project groups on Canvas so that for your algorithm choice and proposal assignments, then you only submit one. Only one person will need to submit. But for this assignment, make sure that both team members submit so that I can confirm that everyone's in agreement. I recognize that since there's an odd number of students in the class, that there's probably going to be one three-person group, but I can't say what that three-person group is going to be. So basically, after everyone turns in all of these, then if there's any singletons left over, then I'm going to have to go through and find a place for them to go. And so I'm going to try to minimize the number of three-person groups, or ideally bring it to just one. So as much as possible, try to form that group with your ideal two-person group to make it easier on me when I, eventually come down. Eventually, there probably will be one three-person group, just due to numbers. But so that's due again this Saturday. If you're having trouble finding a group member, that spreadsheet should be one place to look. Of course, you can also post something on the discussion boards or on Slack. That's fine as well. Then your algorithm choice, that is due basically a week after that. I'm not looking for much there. You can basically say that, you look through that list that I posted. So there's a document of candidates there, and that document of candidates also at the top gives just more information about this final project in general. So you can choose one of those candidates and submit it. If there's something that's not on that list that you feel is relevant to this class, so a nature-inspired algorithm that an AI or optimization that I haven't, what we don't cover in this class and was not on that list, that's probably totally fine. Put it down and I can, if it works for me, then I'll check it off. If it doesn't, I'll give you feedback. Or if there is something we have covered in this class, but you found an extension, that this particular type of algorithm is extended in this different way, in a significant, non-trivial way, that might also be appropriate as well. But the only thing I just want you to avoid is something that something you could have done on a mini project, just like one of these kind of relatively simple canonical algorithms that we've gone in class that even if you apply it to an interesting test case, an interesting system, it still, if it's basically the same thing you could implement it on a mini project, then that's not quite what I'm looking for. So I'm looking for something that's going to drive you to go and learn something about a new algorithm and apply the kind of background context you've got in this class to sort of better understand where it's coming from, what its strengths are, what its weaknesses are, and so on. So that's kind of the goal there. And I do want to, I guess, emphasize that for your the final project deliverables, that the report, it's this like 4-page extended abstract. And the goal here is for you can use off-the-shelf components for the stuff around the project, but around the algorithm. But I want you to actually have a shot at implementing these algorithms. So it's as if you picked up a paper where somebody had published on a particular algorithm, and rather than just taking Python API that they've put on GitHub and just using it, I want you to actually take an attempt at building a sort of simple version of that algorithm to show me that you know how it works and that you can demonstrate some feature of it. So that might mean that you don't implement every aspect of the state-of-the-art version of that, but you've at least demonstrated that, the general dynamics that come out of that particular algorithm. For the presentation, because I'm asking you to do this extended abstract and then a presentation, that doesn't have to have a live demo in it or anything like that. It's basically just like if you were presenting your extended abstract as, in a conference or something like that, in like a 10-minute talk, then how would you do that? So the idea is that at the end of the semester, you'll get randomly assigned a couple of classmates' reports and presentations to peer review. So you'll have to read, 2 reports or something like that, and then watch 2 of these presentations. And so the presentation it's not necessarily coupled with that report. So how can you capture all the salient features of your report in that presentation form? And that might mean that you show off visuals. Maybe you do have videos or something like that, but I'm not looking for you to show me your training session or something like that. Like it's still meant to be effectively an executive summary of the extended abstract that you submitted. So that's kind of everything that's expected here. Then, on the shorter term, Muddy's Point Sunday, concept check Sunday, mini project Sunday. I'll go over this concept check and make sure there's none of those. I know that at the last concept check, I guess there were a couple of these drop downs that were a little longer than some browsers liked, and instead of wrapping, they just cut them off. And if that's the case, then I'll go and I'll add post something in there to make that easier. But on the browser I use, they don't do that. So I use Arc, which is based on Chrome. But I guess Safari that had that particular issue. So I'll try to go through there and make sure there are none of those, and then add something in case there are. So I think that's all I've got. So any questions? Okay, great. So where we took off last time is we just defined entropy, and we're moving towards applications of entropy in machine learning. And so I mentioned that when we talk about entropy, what we're really trying to capture is the it's effectively the number of microstates in a macrostate. And so we talked about the if you had an example like this one, where you have a box, a room like this, and if you have a bunch of gas in the room that is all clustered in one side versus another room where you have things spread out, then if we kind of call this macro state spread out or equal density, and we call this macro state clustered or corner clustered, then effectively there are fewer microstates here and more microstates here. And so there's more ways to be spread out than there are to be clustered. And so the number of microstates, if we call that W, so I'll say number microstates, we'll say is W. Then the entropy we define as S is equal to log W. And so over here, S is also equal to log W. And then we can see here that this entropy is going to be less than this entropy because the W over here is less than the W over there. It's just a monotonic transformation. Does anybody know why the physicists and everyone else use a logarithmic transform of the number of microstates? Why log? That's a clever answer and you might think that is the reason that there's some sort of exponential scaling, but there's something a little more fundamental, something a little more simpler, something kind of computational about it. There's some nice arithmetic or nice some properties of the logarithm. So the thing about entropy is when we combine systems together, it would sure be nice if their entropy would combine in a convenient kind of way. And so if you have if you have one system that like I've got the entropy in this room, right? Well, there's also entropy in the room over there. Now, if I were to calculate the entropy in the building, wouldn't it be nice if I could just add up the entropy of all the rooms? Now, what is the number of microstates in this building? it is the product of microstates in this room times the product of microstates in that room times the product of all the other microstates in all the other rooms. It's the Cartesian product of all the things that could happen here and all the things that could happen there. So if this is an isolated system and if that room over there is an isolated system, if I want to know what the entropy of the combination of those things are together, I'm just going to multiply the number of things that can happen here by the number of things that can happen there. So that's how I get my number of microstates, is through multiplication. But that's kind of annoying to say, like, well, if I had 5 microstates here and 5 microstates there, then there are 25 different ways that this building can exist. You know, that multiplication, this kind of gets to the exponential thing, is it's sort of ugly that it scales that way. Now, if we just define entropy as the log of the number of microstates, then what happens? What's the entropy of the building relative to the entropy of all the individual rooms if we make it the log of the number of microstates? It's additive, it's a sum. That's why entropy is the log, is it allows you to add systems together and have their entropies add. So if you have the entropy, if I've got number of microstates in system A times number micro in system B, then that gives you that that's the total micro in A combined with B. I'll say A with plus B. I'll just write plus B. But then if I do then the log of that, of number micro, number A times number B, then that's going to give me the log of the number A plus the log of the number B. And so add additive entropy. So that's a nice feature there. So that just makes it easy to add these systems. So there's a bunch of products that come up. So we use the log because whenever you see a bunch of products, it's easier to use a log to turn it into addition. So now we'd like to generalize this a little bit further to say now this is when all of the microstates are equally likely. So we can say that there are very few configurations where there are very few microstates representing states of this room where all the gas is up into a corner. But they're all equally likely of all of those ones that are there. So it's like they're either 0 or they're 1 over that number of states. So right now we're sort of assuming that there's a 1 over W probability of any one of those microstates, and there's a 1 over W probability. I guess I call this 1 over W small probability and 1 over W large probability of each one of the different states that this room could be in the clustered or non-clustered. Now, to generalize, you could say, well, let's try to think about the entropy of a distribution where each microstate could have a different probability. So it might be that rather than just saying that there's some that are 0 and some that are uniformly distributed across the rest, what if we just said, generally speaking, there's all of these different configurations, and we can now put different probabilities on each one, and then measure the entropy of the resulting distribution. How would that look? And so the idea there is that entropy of a distribution and so if we have microstates, so that there's like a certain number of microstates, so I can say that there's like a probability. I'm going to say right now, I'm going to consider this discrete. So there's a probability of being in microstate I. So this is, I'll just, probability of being in microstate I. I can allow that to be any probability, and then I've got this distribution of probabilities. So then the entropy of the distribution, I can write in this form where I'll say it's the sum, and I'll just maybe shorten this to say this is PI. So P sub I is the probability that I'm in microstate I, and I'm assuming that there are, I'll say I there are n microstates. So I is in the set of 1 to capital N, or out to capital W, to be consistent with what I had in the previous page. So then I'll say S is equal to the sum of PI log of, let's see if I want to do what's going to be easier to think about here. I'll do 1 over PI for now. And so this formula here is the same as I just wrote down if they were equal probability, if you think about it. So this here is basically the expected value of log 1 over PI over this distribution. And so, well, why 1 over PI? Well, if these were all equally distributed, then PI would be 1 over W. So 1 over PI would just be W. And I would end up, so like if this is so if PI is equal to 1 over W, then we have S is equal to the sum of 1 over W log W, which is just equal to log W, which is the same as we got before. So that's our generic form of this. And so that we just basically imagined that we kind of clustered. If you imagine that rather than saying I've got a bunch of microstates that are equally likely, you could say that, well, what if I clumped some of those microstates together? Then you can kind of end up building this thing where you kind of each microstate kind of has it has a multiplicity, and that ends up sort of setting up this kind of ratio here. But it's just a generalization of this idea here, is that if every microstate's equally likely, it's just the log of the number of microstates gives the entropy. If they're not equally likely, then this formula here. Now, this formula here, I can simplify to have a negative out front, and then it becomes PI log PI. So I just took this is just the inverse, pop the negative up top, it's a logarithm, pop it in the front, and then that is our more sort of, simpler here. Now, this log is currently, now I could scale this. I could add some KTs and things like that into that, but right now this is the natural log. That's the physicists like to use natural log. We can also just change the base of that algorithm because it just scales the units. And so what we often will do is say use log base 2 instead of natural log. And so, this here I'll just mention physics log equals natural log. So if we use log base 2, we get the same sort of formula here. So we have the entropy in terms of PI, so I'll put a negative out front, log base 2, PI. But then now this is in units of bits. And so that's kind of nice because in this framing, it tells me how many bits do I need to encode the information left over once I've accounted for the macro state. So if I know that my macro state is everything's clustered in the corner. And I could say, well, how many different ways can you be clustered in the corner? And I could say, well, there's 1,000 ways you could be clustered in the corner. Well, if I wanted to know which of those 1,000 ways to be clustered in the corner, I would need 10 bits to do that, because 2 to the 10th is 1,024. So if I had 10 bits, then I could index each different way that you could be clustered in the corner, and I could give them an ID. Now, if I allowed the gas to spread out, and now there's, 1 million different ways to be spread throughout the room. Now it's harder for me. I can't use 10 bits to specify all of them. Now I need more bits for that. And so that expansion, that additional uncertainty that has been added to the macro state, can be modeled by the additional number of bits that you need to encode the state of the world given this new macro state. So that's what's happening as time is evolving, is you're erasing your history and adding uncertainty. And the amount of uncertainty that you add is this rate of entropy increase. So when we say the second law of thermodynamics, is delta S is greater than 0, what this is meaning is that this is a rate of erasure of information by time. And so macro states become less informative. And we can measure how much information we lose by measuring the change in bits from one to the other. When the universe started as a ball, with all the mass was concentrated in one particular point, there was one configuration of the universe, basically. It's maybe not just one, but there were a very, very small amount. And it was a singularity, we think. So the point is there's not a whole lot of universes that can exist with all the mass clumped into one spot. You don't have any degrees of freedom left over. So once you say all the mass is concentrated in one place, you're done. That has zero, it's basically log 0 is 1. So it has 1 bit, are you there or not? But that's it. So there's that, you don't need any other information. All you need to know is that we're at the start of the universe. But then as the universe clocks on, moves farther and farther away, then things start to spread out in random ways. And as they start to spread out, that like, oh, well, if you're a second away from the Big Bang, then now there's a lot more uncertainty. You can say, well, I know a lot now that we're a second away from the Big Bang, but now there's a bunch of stuff that I don't know that I used to know. And so can you be more specific? All right, we're a second away from the Big Bang, and here's the positions of where things are. Now we're 1,000 years from the Big Bang. Now we're 1,000,000 years from the Big Bang. As you get farther and farther away from the Big Bang, it's less informative to know how far you are away from the Big Bang. So you're erasing your history, and the number of bits you're adding as time goes on is effectively a quantification of the second law of thermodynamics. So, and that's just randomness, just the fact that it's hard to go. It's a ratcheting effect, because as as things randomly move out, it's very unlikely they're going to reverse themselves. And that random expansion is what we see there. Okay, question. Yeah, right. I mean, the state that came before, there is this natural asymmetry that states before have are more informative. Macro states before are more informative than macro states later. Yeah. Yes. Well, that's the you're you're not getting spread out because you're increasing degrees of freedom. So initially, like, if you say, if I took a bunch of ping pong balls and I held them all in one spot, And if there were four ping pong balls and that there were the four colors and I held them in a particular spot right here, there was ordered. So that order, then as long as you knew like you need to know the initial order and the height them at, and then that's all you need to know. Now, when I drop them, a bunch of stuff happens where at that point, in order for me to know where the ping pong balls are, it's not just enough to know that there were four colors of ping pong balls that were originally in that position. Now, there's in order for me to understand the ping pong balls, I have to explicitly encode their relative positions from each other, and it just gets more and more information it has been added to the system, and I've lost that order. So this is sort of a loss of order, a loss of patterning is sort of what I'm trying to communicate here. And that's and this is connecting to in machine learning is a loss of bias. And so there are distributions that have effectively been shaped by more than just the constraints of the world. They've been arbitrarily shaped. And those additional shaping of the distributions introduces bias, it introduces order. And if we are trying to make a machine draw from a random sample, we want to make sure that it only is reflecting explicit constraints, not implicit constraints that come from the shape of the distribution. That's where we're getting to here. That's the reason why I'm not just trying to get philosophical. I'm going to tie this back to machine learning. Yeah. Yeah, if you took a snapshot, where's all the gas right now? And what's all the momentum of every molecule? That would be the microstate of this room. And then just due to random thermal agitation, there's another microstate that this room might be in next, but it's just equally likely it's in that kind of spread out versus the other spread out. Now, the microstate where all the gas in this room suddenly shows up in that corner, that's not very likely. Any other questions about that basis sort of foundational idea? I don't want to say basic. Okay. Yep. Sorry. A macrostate is a distribution of microstates. So that can be our new kind of definition here, is that a macrostate is a distribution of microstates. And so there's a macrostate that corresponds to this chair. There are a bunch of different ways to have a chair. Um, and actually they're the if we think about the momentum of particles in this chair, you might actually be moving through different microstates over time. But there is one macrostate that is chair, and there is macrostate that is, and that's one of the questions is like, what is the distribution of air in this room that we would expect at equilibrium? And what the second law of thermodynamics says is that we would expect at equilibrium that it is going to be the most informationally rich distribution. The second law of thermodynamics says that no matter if somebody came in before this class and they screwed around with the air in this room, they somehow swept it all over there and swept it all over there, and they said, aha, it'll be a vacuum, people will walk in here, it'll be a big disaster or something. Well, we know that very shortly the air would just fill things, because that additional, like, to me, all I need to know about this room is it's got, four walls, a ceiling, and a floor. And then from there, it's a pretty darn good guess that air will be uniformly distributed throughout the whole room. Why do I mean it's a pretty darn good guess? The second law of thermodynamics says it's a pretty darn good guess. Because if you were to arbitrarily say, well, even though there's not a wall here, I'm going to compress all the air with like some temporary piston. I'm going to move it all and I'm push over here, and then I'm going to get rid of the piston. It would be crazy to think that the air would stay over there. It, though on a small time scale, some of the air is going to move this way and some might move back. At a small time scale, it may actually stay just over here. But over time, that we're going to expect that the microstate, the distribution of air that is highly, compressed over here is going to be unlikely, and the and so the certainty I have about where the air is needs to go away over time. So at equilibrium, which is why this is going to eventually relate to simulated annealing, but we're going to take a sort of meander through machine learning first. At equilibrium, then we would expect the best way to distribute these microstates would be the things that only have information about the walls. Like, if there's any other historical information that, like, well, there was a class before here where they did all of these different things. Like, well, that's kind of biased. Like, who cares that there was a class before here? Generically speaking, if I need to model where the air is in this room, I really need that model to be just on the walls, just on the physical constraints of this room. Anything else that you say, yeah, physically it is possible for the air in this room to be just over there. It's possible. I'll give you that. But if you choose that distribution for your sampling distribution in your stochastic model or whatever you're building, I'm going to say, why did you do that? It's so biased. Why are you so interested in putting the air on that side of the room? And it wouldn't make any sense. But if you would have said, no, I'm going to spread the air out completely, I wouldn't even think. I'm like, okay, I'm not even, and the reason why is due to the second law of thermodynamics. We know that when you look at a distribution and you see an arbitrary choice made where another choice could have been made and it would have met all of the constraints, then you know that, like, that's weird. Why did they do that arbitrary choice? So when we choose distributions, we need a mathematical process that tells us that this is the least biased distribution. This is the distribution most likely to be produced by the erasure of order that just comes free from the universe. And that's why we have maximum entropy methods in machine learning. Okay. So any other question about this sort of basic backup here? What I mean by bits in the microstate, macrostates, and all that. Great. So what do we do with this? So for example, in a bunch of, so in sort of good old fashioned AI, natural language processing and things like that, these methods, so this is my introduction here to maximum entropy methods, or MaxEnt methods, became very popular to make realistic predictions based on data and constraints from prior information. And so generically, I can say, like, for example, let's say I had a constraint that I want to find the distribution. I have a single variable distribution where I've got this constraint that it's a distribution on X, and X has a lower bound and an upper bound. And I would like to find the maximum entropy distribution. So there are a bunch of random distributions where that is the case. A beta distribution with the right scaling does that. There's all sorts of things at these finite bounds or whatever. A uniform distribution does that. There is a process so calculus of variations. I'll just write this here. So I'm not going to do the math. So, and that allows you to solve for the maximum entropy distribution. So calculus of variations, like normal calculus, I could say, what is the value of X that maximizes a function? Well, you can actually do calculus over the space of functions. And calculus of variations provides one way to do that. So I can say, given that I have defined entropy, so if I've got my little S is equal to minus the sum of pi log, I'll say log 2 pi. If I have that little definition of entropy over here, and this does generalize to continuous as well. So I could make this the integral of the density function times the log of the density function. Works the same way with the minus out front. So I can say I want a distribution whose probabilities have this property and solve for the distribution that maximizes this property. There are mathematical methods from calculus of variations that do just that. And if you were to do that, then what you would find is that the maximum entropy distribution is to have X distributed as a uniform distribution between your lower and upper bounds. So I think that kind of makes sense. And again, going back to the bias, I mean, this is what again, by MaxEnt, I mean, this is what I'm calling the least biased. So this is claiming that in terms of entropy, and I would say in terms of what most people would refer to as bias, that anything else that fits those constraints would raise questions about why you chose that and not the uniform. This is like the null, so if you chose some beta distribution that had a peak at one end and it was bimodal or whatever, then that implies there's some other constraint coming from the head of the programmer or the statistician or whatever. So this is the thing to say, that if you choose that distribution, it is only based on that constraint. It is not based on hidden information, hidden constraints in the mind of the person that is doing it. That's what I mean by MaxEnt. We can do that with other types of constraints as well. So we can say, and this will start, and if you've never heard this before, then this will start maybe making some sense over why certain models have certain structures, that why we take those for granted. So if I have the constraint that let's say I want to spread particles out, their positions out on a line. And so I know that the distance between the particles has to add up to the length of the line. And that's my major constraint. So I'm going to say that the sum of the distances in between particles. So if I've got n particles, one of them starts at the very end of the line, and then d is the distance after it. So I'm basically drawing random distances that I put between particles so that all these distances add up to L, and I've got the constraint that di is greater than or equal to 0. So this is like spacing items on a line of length L. Now, if I am to do that, and this, by the way, if you think about it, this is equivalently, I could have said that I want the average value of these things to be a particular constant. So I'll say L over N. So it turns out that what I'm about to say here also applies that if you have fixed averages. So if you have some sort of quantity that it's either you're conserving the quantity, this is a conserved quantity constraint. So there's conservation constraint or a constraint on the arithmetic average. It works the same way. And for both of these, anybody guesses what the MaxEnt for this is going to be? Well, what would be the I'm looking for the L by N, but what distribution will be? What's the random distribution? What's the probability distribution that will maximize the entropy here, given this constraint? Of all the probability distributions that have these properties, what do you think is the one that maximizes entropy? Yeah, the distribution. Like here I said the uniform distribution. So does the normal distribution do this? Huh? You think it's a uniform between like this that goes to infinity? So uniform between where and where? 0 and L, but I mean my distances. Well, okay, that's true. That I guess the distances have an upper bound and implicit upper bound of L. So that is true here. I'll give you that, but that's not actually the one that I'm looking for. What I'm looking for is actually here is that if you solve for a constraint like this, then the exponential distribution is the one that has the least entropy. So di is distributed as an exponential with mean L over N. And so in other words, what I'm saying is that the probability distribution for FD is just L over N times E to the minus N over L times D. So exponential. So this is a Poisson point process. So Poisson point processes are spaced out by exponentials because, well, you could say for a number of reasons, but one of the things that relates to that is it's the maximum entropy way to do it. If we all, I mean, probably very few of us are carrying a lot of cash on us, but if we all, all of us in this room got together and we summed up how much cash is in this room, I would hazard it's probably like $2, but let's say it's like $200. We could call that 200 here. And then each one of us, this is how much we have in our wallets. If we were to randomly bump into each other and trade, just draw a random amount and then just trade, I'll give you $1 and you give me $2, whatever. And we do that over and over again. And then we calculated the distribution of money that's in our wallets, exponential. So there would be, most of us would have very little in our wallets. Some of us would have a lot in our wallets. The uniform would not be the distribution. So that process there would not end up making us all equally rich. It would actually create a bunch of poor people in this room and a very few number of rich people in this room. You can do that. Really easy to do exactly that experiment. Go into MATLAB or Python or whatever after class, try exactly that experiment, and then do a histogram, and that's what you'll get. This is also related to the Boltzmann distribution, which we'll talk about when we get back to simulated annealing. Similarly, if I were to do time between arrivals, at an airport, for example, so given an arrival rate. So if somebody tells me that the average arrival rate is that the expected time between arrivals is some average arrival rate mu, and I know that all my times are greater than or equal to 0, then for similar reasons, that time is going to be distributed as an exponential with mean mu. And so what we're saying here, how many people have heard of the Poisson process? Anybody? So a couple there. So what we're saying here that a Poisson process is a counting process. So it is a process where you say how many people have been counted up to this point, up to this point, up to this point, and that count is distributed as a Poisson random variable, but the time between counts is an exponential random variable. So the Poisson process is the least biased distro of arrivals. So this, among other things, like we give all these reasons for why we choose the Poisson process. We say like, well, if there's independent arrivals and all of these, we give all of these things that if you have all these things, they're actually, if and only if, like they're equivalent to the Poisson process. But then you'll find people that when they really scratch their heads, they're like, well, arrivals are never independent, exactly, and all of these other things, and say, so it really is the Poisson process, which in a bunch of different modeling, you go queuing theory, networks classes, or whatever, you're going to talk about Poisson processes. It's how we model stuff very often here. And you'll say, but it can't be right though, because all these assumptions are not quite met. But then I'd ask you, well, what's better? Anything that you choose that's not the Poisson process is based on your anecdotal sort of insight into the system. And that might be good insight. And if those are real constraints that actually relate to that system, then write them down and then solve for the MaxEnt for that. And you might get something that has a different distribution of inter-arrival times. If we model how how frequently buses arrive, it's not going to be a Poisson process because they're on a schedule, right? So so the Poisson, so an exponential has this memoryless process. You do not have a memoryless process of the bus. If you've been waiting 9 minutes, there's a good chance the bus is going to come in the next minute. So it does not have, it has memory. So a bus would be a bad thing to do for. So we could do different constraints and then get a distribution to describe how the bus arrives. But if you're just talking about like, the airport, people just arriving at the curb at the airport, then a lot of times this is the best you can do without introducing hidden biases. And that's the reason why we use these so much, is that they're the least biased distributions. Based on everything I know, a manager at the airport told me the average arrival rate for this time of day. I know that arrival rates have to be greater than or equal to 0. I ask them to give me anything else. And they come back to you and say, sorry, that's all I got. If that's all you're giving me, the most honest way that I can model that system is by assuming that our interrivals are exponentially distributed. Anything else, if I choose uniform, whatever, I'm adding information that was not given to me. Does that make sense? What I mean by least biased there? So when you're doing stochastic modeling, when you're choosing your distributions, you can look up what is the maximum entry distribution for these constraints, because most people have solved these problems already for you, and and then choose one of those before you just go off and choose something arbitrary. All right, so how does that relate to say natural language processing? Oh, I guess I should throw one more in there. Okay, so what about, here's my constraint. I know that the expected value of X is given. And I know that, I'll phrase this, the variance of X or standard deviation is given. So these are my constraints. What is the MaxEnt? Any guesses here for when it's the value of X could go anywhere from negative infinity to positive infinity, but we've been told that the mean is given and the variance is given, and we want to choose the least biased distribution that has these two properties. Normal distribution, right? So that's one of the ways you get the normal distribution. So this is a normal distribution with those two parameters. So Gaussian or normal. That's one of the things. I mean, another place where this comes from is the central limit theorem. But that's also the beauty thing about the central limit theorem. Like, again, view the central limit theorem through the lens of the second law of thermodynamics. I keep walking back and forth across here. If you lift up this carpet and there's a carpet pad underneath there, it's going to have a wear pattern. That wear pattern is going to have very little wear up here because other instructors don't walk here very often. I walked up, you bring your legs in, it makes you uncomfortable. And very few instructors walk back here, right? And so there's going to be a wear pattern. And if you took a cross section of that wear pattern, it would be a normal distribution because it's additive wear. And the central limit theorem says if you add a bunch of independent random variables together, then the distribution of their sum is a bell curve, is a normal distribution. And really, though, another way to view that is I know the average. On average, people walk right where I'm walking. And I know the variance. So I know that based on the structure of the room, they generally walk to here, they very rarely walk to there, and so on. So if I know generally the spread and the average here, over time, I'm erasing history. It's just entropy happening. So just like the particles in the room, then we can say what happens over time to the wear pattern. Well, it's going to erase the history of any individual instructor, and it's going to freeze this tendency in such a way that the wear pattern is going to be a normal distribution. It is the maximum entropy distribution in wear patterns is the normal distribution, which is why we see it everywhere. That's why in the door, if you look at a door, it's going to have a dull spot in it. And that dull spot doesn't tell you anything about any individual person that has used that door. Now, a clean, like fresh door is going to have a fingerprint in it. It's going to have a handprint. I mean, then you're going to, I say, that looks like Ted's hand. Ted was here. But you come back a year later and all that's going to be wiped away and it's just going to have a dull spot there. And I have no idea who was there. But I know a lot of people were apparently here and they generally push on it right there. That is exactly the same thing as particles of air just diffusing and eventually filling the space. Here, the maximum entropy distribution is air filling the whole space. On that door, the maximum entropy distribution is a wear pattern that has a strong spot in the middle, and it fades off. Same thing, it's on the carpet. So this is sort of your basic, entropy stuff. The natural language processing people then made this popular in machine learning, and then it's gotten a lot more popular in other things since then, because they wanted to predict the next word, so again, this is good old fashioned, and now we have all sorts of other ways to do this, but this was decades ago. You might know, for example, that you've got a 40% chance of getting the article a or an, and you might have a 20% chance of the next word being the, um, and um, and then so you could say, well, then what is the best distribution for picking the next word? Well, you could imagine doing this do for um, a whole dictionary. So if you had a corpus of text, so you've got all the words in the dictionary, and you've got a bunch of different text, you could just count up the distribution and say, how often do I get an A? How often do I get an and? How often do I get a the? And so on and so forth. And but then there might be some things that you don't end up getting a good estimate from. So there might be some degrees of freedom left in your distribution. And so then you have to say, well, how do I choose a distribution over the whole dictionary of what words to choose next? Well, you could take these as hard constraints. I need to consider every distribution that has 40% a and 20% the. Well, there's now 40% left over that I can distribute around words that I don't have data for. So I would then maybe ask, well, what's the maximum entropy way for me to distribute that probability around those other words? And so this can get more complex here, but the point here, especially when you get combinations of words, then the point here is that you can use constraints in the language and frequency distributions estimated from the language to come up with prior information, and then whatever degrees of freedom are left over that are your design, like you're trying to design a distribution that chooses the next word, then you can choose a maximum entropy distribution, which will then minimize the bias in the choice. It says, I don't really have any other info. So it might be that, if that for this particular sequence of words, the next word could be one of these 10 different words. The maximum entropy suggestion is that it's more likely to be this word than that word, similar to like the normal distribution. Like I know that based on the constraints of this room, that it's more likely that the next instructor is going to walk here. And so if I'm trying to simulate another instructor next, I should probably have them walk closer there, but I'm going to draw it from a bell curve so that some instructors will walk over here, but they won't be very likely. We can do the same thing with text prediction and other symbol prediction, is that you take constraints that shape and that are hard constraints, and those hard constraints again may not be constraints on the symbols. There might be constraints on the combinations of symbols, where it leaves you degree of freedom. Whenever you're left with degrees of freedom, where you're now causing a machine to draw from those degrees of freedom, you can use MaxEnt to say, what is the maximum entropy, the least biased distribution across my degrees of freedom to draw from? And that's usually the most honest way to do things. So now people use MaxEnt for all sorts of other things. So there's like MaxEnt methods and so are often written MaxEnt in, for example, anthropology and psychology, or anthropology and ecology. So as an example, you can, for example, go out to an area in the ocean and say, where have whales been sighted at this time of year? And you use then geometric constraints where the water is, where whales have been sighted before. You throw all this stuff in, and then you can you need to decide, well, if we need to go and find the next whale, maybe tag them, where, given there's a lot of water, where's the most likely place for me to go? And you can build MaxEnt distributions of where whales are going to be based on information about the geography and where whales have been in the past. And you combine those things together, and then it tells you, aha, I go to this area here, and most likely I'll find whales. Anthropologists have done this to find artifacts. They've said, we went out in the forest, we found a bunch of these clay pots in this particular area. We want to figure out where to dig next. We have a limited budget. They've used MaxEnt methods to predict where to dig next. And it turns out that they do end up often finding new artifacts where these MaxEnt methods sort of tell them that they should go. So that's sort of the way these kind of entropy-based approaches, which again, just describe why gas in this room is spread out, also tell you where you should sample. All right, so that's MaxEnt methods, and I want to get back to simulated annealing, but so any questions then about that? Sort of physics-based question? No, it's based on well, whatever constraints you have for the language problem that you're so there are MaxEnt libraries that are out there. So you can go out and download, Python MaxEnt libraries. And then in those, they will give you the ability to specify prior information. It's very kind of Bayesian, so they give you the info to sort of specify prior information and constraints, and then it will then go out and construct for you a MaxEnt prediction. So it isn't quite as, these are sort of toy problems. Like if the constraints on were this simple, then you could do it by hand and do here. But you can numerically solve for MaxEnt as well. And so you can get very complex sets of constraints, throw it into a MaxEnt library, and then it will then draw for you predictions out of that. And you can do that, like I said, for a lot of these different spatial things where you're like, I don't know where to go next. What's the best way to predict where to go next in this spatial search problem based on the constraints of where I can go, where things actually could be, and where things have been found in the past. And then, come from there. Okay. So how do we get back to simulated annealing? Now, remember, the reason I went down this path, well, in part was to show you that physics has been extremely influential in AI, and it will, in a second here, you'll actually see, if not here, then on Tuesday, you'll see that physics has been extremely influential in very, very common methods that a lot of you pop it. So any of you that have built a deep network, a deep neural network, there are certain modules that you probably all use very frequently that were invented because of entropy, that were actually invented to mimic these processes. But for whatever reason, they don't name them that way. And so when you actually hear certain names, you have no idea that it's kind of ironic. They've erased their history. But in reality, if you look up where they're from, you find out that the way they came up with these was by looking to the physicists. So let's look at that. So remember, we're going back to thinking about, in simulated annealing, how to simulate the we have so recall simulated annealing, which I'll abbreviate SA. We've got configuration, so candidate configurations of our design problem. And these are our microstates. And we have an adjustable temperature. T. And we would like to use a physical process to search the design space. And here, what we're going to do is to set things up so that energy in our simulated process is proportional to our optimization objective, so that minimizing energy is equivalent in our simulated system to minimizing our optimization objectives, which I guess I'll call F, or I'll try to call F. And energy, I'll call E. So that's our goal with simulated annealing. And so the question here is, how do we emulate or simulate microstate changes akin to physical system processes, I guess. Well, if all we've got here is temperature, then our constraint is that the average energy is equal to K times T, or I'd say the average energy is proportional to temperature. This is average energy. So we can then ask, what is the MaxEnt distro given temperature? So for a given temperature, what microstates are accessible to us in sort of an unbiased, physically similar way? And so if I solve that problem, which we kind of already have, then what we find is that if our mean, so the constraint here is that the mean energy, this is energy, of our microstate, I'll call it state I, so this is our candidate configuration of our system, is equal to KT, so it's equal to some constant, then the MaxEnt distribution is something that looks like this. The probability of state I is equal to E to the, and I'm going to call EI is, I'm just going to say is the energy of state I, or I'll call it E of state I, just to make it easier on my hand to write. So E to the minus EI over KT divided by the sum of E to the minus EI over KT, and maybe I'll make this J just to make it, and then this is summed over all of the J states. So this down here, we're going to call a partition function, sometimes called Q or Z. And it's just a normalization. So basically, the idea here is that we've made the probability of state I proportional to E to the minus EI over KT. And then we had to normalize the whole thing so that the sum over the probabilities equal 1. That's why it takes this form. And so this is a Boltzmann distribution. Which is also sort of exponential in energy. But when you look at this, and so what this does here, what's this says is that states with lower energy are more likely. And it says that as t goes to infinity, then all states become equally likely. So if I make this thing hotter, we can reach all states. If I cool it down, then only the lowest energy states are the ones that are more likely. To those of you who've done some neural network stuff, does this look like anything you've seen before? And if so, what does it look like? It's not hard, but it's soft. Softmax. That's where softmax comes from, the Boltzmann distribution. Softmax flips the sign of this to make it positive. In a softmax, then the bigger numbers are going to produce higher probabilities. Here, the littler numbers. So if you view here, basically, this is like, this is like softmax, or I'll call it softmin here. So your inputs are your energy states, and the output is probability. And so large energies will have low probabilities in a soft min. Low energies will have high probabilities in a soft min. If you get rid of the negative, then your soft min becomes a soft max. And then high energies give you high probability, low energies give you low probability. And if you want to change things to bias things so that you allow for things to be more spread out or whatever, you change temperature. So likewise in softmax, you can, you can set KT equal to 1, or you can take KT and you can, that scalar there, you can scale it so that it makes your softmax kind of flatter or peakier. So that's where the machine learning people got it, is they said, this distribution of microstates is pretty convenient, and it's got this cool parameter that allows us to flatten it out. This sort of feels like a softened version of an argmax. So rather than just taking the max, it allows us to sometimes take things that are less than the max, or in this case, sometimes takes things that are greater than the min. But most of the time take things that are at the min. But we can adjust how biased it is towards the min by adjusting the temperature. And that's where they got softmax. Questions about that? That makes sense. So what we then want to do is use this distribution to guide our random search through the space. So what we really want to do is to say, if I'm at a particular point in space, I want to decide where I could jump. So I'm at this design space. I have this robot that has this length joints and this much power to its motors and whatever else. Here's a robot with a different length joints. Here's a robot with different sets of motors. Here's and so on and so forth. So I'm walking around my design space. And so as I'm doing this search, I need to say, how likely is it that I'm going to walk this way or walk this way? So this is my fitness calculation. So I'm going to try here, and then I'm going to decide, should I stay here or go back to where I was? I want to use the Boltzmann to basically say, how often do I accept this position? Sometimes, even when this is a worse design, I want to accept it because it allows me to find designs that are much better that are way over there. So how do we do that? We're just going to basically say, I want to compare state I to state J using their delta energy. So basically I'm saying delta E is going to be equal to, and let me make sure I get my, I'll call it delta Ji, and I'll say delta Ji is equal to Ej minus Ei. So it's the energy difference between them. So if we say the probability of state J divided by the probability of state I, well, that's going to be just equal to E to the minus delta Ji over KT. So does that make sense? So that if we take the Boltzmann, I'll flip over there real quick. If we take this distribution, we're going to divide this by the other one. These guys cancel. And then I just combine things together so that it's in this nice, convenient little package. So this here, this number is a likelihood ratio of one state relative to another. So this provides a suggestion for how we can search through our space. And so what we'll pick up on the next time is to actually build this into an algorithm where we're going to propose a distribution, and then we're going to calculate this likelihood ratio. And if this likelihood ratio is 1 or higher, then we just take the proposal. If this likelihood ratio is less than 1, then we take that proposal with that probability. And that's basically what simulated annealing does. That plus a schedule that changes this temperature, making proposals more likely or less likely as the temperature goes up or down. And that's all I've got for you. I don't want to keep you here too long. So any other questions, feel free to come up. Otherwise, I'll see you next week and have a good weekend. I'll make sure that that concept check is properly scoped for what we've covered and doesn't have any of that Safari business in it.